Hello folks, this is Sridhar Ramakrishnan. Welcome to our webinar this month. Thank you all for joining. Before we get started, a few bookkeeping items as usual. The presentation by Dr. Umesh Krishnaswamy will begin shortly and go on till approximately 1 p.m. Umesh has consented to stay on for a little bit after 1 in case there are any questions and follow-on discussion. The slides and the recordings will actually be available at the end of the presentation. Log into your account to see them or on our YouTube channel, the link of which is available at our homepage. As a matter of courtesy and etiquette, please keep your telephone or microphone muted at all times. Only unmute yourself to ask questions. If you have dialed in, as I've mentioned before, to the conference by the phone, you must have entered your audio PIN. I can only unmute you if you do that. For those of you who prefer to ask questions by instant message, there's a chat window. Please ask your question there. Umesh has indicated that he welcomes dialogue and questions throughout the presentation, and I'm looking for a nice interactive session here. Okay, with that, I guess let's go ahead and get started. Today we are delighted to have Dr. Umesh Krishnaswamy to talk with us about ONOS, an open source distributed SDN OS. As you all know, you can't go anywhere today without hearing about SDN, so I thought it's a fantastic opportunity for us to hear about it from Umesh, who's done some pretty interesting work at OnLab. Dr. Umesh Krishnaswamy has 17 years of experience in leading industry technology teams and developing carrier-grade networking products. Umesh is currently a network architect at Open Network Labs, a nonprofit lab that develops, distributes, and supports open source tools and platforms for software-defined networking. At OnLabs, Umesh leads the development of ONOS, an open source distributed software-defined network OS, and SDN IP, an application for seamless peering between SDN and IP networks. Prior to OnLabs, Umesh was at Juniper Networks, where he held a variety of positions spanning engineering to product management, including leading Juniper's incubation lab, working on incubating promising new technologies. Prior to that, Umesh was at HP. Umesh has a PhD and a master's in computer science from the University of California at Irvine, and he also holds a computer science and engineering degree from IIT Mumbai. He has numerous patents in networking, router design, and dynamic optimization. With that, I'm delighted to turn it over to Umesh. Umesh?
Thanks, Sridhar. Welcome, everybody. Thanks for joining. So the title of this talk is, as you see on the screen, is Tools and Platforms for Open Flow-Based SDN. And the slides are organized in roughly about 3 of 4 sections. The first section, just as a brief description about ONLab. Many of you may not have heard about ONLab, so just wanted to go over that. And then afterwards, I wanted to take us one specific problem and then go and get into that one, and then I use that as a basis for describing 2 of the projects within ONLab. One is the Open Network Operating System, and the second one is an application that runs on that network OS or the controller, which is SDN to IP peering. Feel free to ask questions along the way. So ONLab, as Sridhar mentioned, it's a nonprofit lab. It was founded in 2012, and the mission of the lab is to develop, distribute, and support open source tools and platforms for SDN. The current projects that are going on with it, and you can see that one of the questions I commonly get asked is that how is the lab funded? What you can see in the bottom is a set of organizations which have funded, which are the sponsors for ONLab. They comprise of end users and vendors, and then afterwards there's also a second component, which is research grant organizations like NSF and Genie and so on. So that's how that's what gets the funding for ONLab. I'll tell you a bit more about ONLab in just a second, but I thought I'll just give you an overview of the kind of work that we do, and then afterwards the people next. The projects that are currently going on is, the first one is something that, if you are familiar with SDN and with OpenFlow, you may have used it. It's called MiniNet. It is to emulate an OpenFlow network right on your laptop, or if you want on an EC2 cluster, on an EC2 system. The second one is something called FlowWiser, which is used to share physical OpenFlow switches. And the third one, this is the one, it is called Open Network Operating System. It is a distributed SDN controller. It intends to be an open source, like distributed SDN controller. And there's the next one is a project called OpenVertex, which is a network hypervisor. And finally, Open Cloud, which is for doing service orchestration in a cloud. In this talk, I'll mainly be focused on ONOS and or the Open Network OS, and then afterwards applications that are running on top of ONOS. Just to give you an idea of the early SDN activities that ON Lab, or the people within ON Lab were involved in, the folks who started ON Lab are really our Guru Parulkar, who serves as the executive director. And before ON Lab was formed, he used to run something called a Clean Slate Lab in Stanford University. And in Clean Slate Lab, one of the main projects that was happening back in 2007 was the OpenFlow activities around OpenFlow. And so Guru and Nick McEwen from Stanford and Scott Shankar from Berkeley, they were some of the key folks who were working on OpenFlow and in the very early days. And some of the things that the projects that they were involved in were things having to do with like ethane, which is a work that Martin Casado did when he was doing his PhD work. Then afterwards, OpenFlow, FlowVisor, all of these tools got built. And then afterwards, starting in 2009, they focused a bit more on deployments within Stanford and using through Genie, which is a network initiative spanning about 20 universities and 20 campuses to get OpenFlow deployed. And so there were a lot of deployments going on, and then afterwards there was a bunch of demonstrations that they did. All of those things to kind of show what OpenFlow-based SDN was capable of. And then afterwards in 2012, sometime in April of 2012, decided to form this organization called Open Networking Lab because they felt that the community required a permanent organization to support these tools and platforms that they were building. Previously, the tools and platforms were being built by graduate students, and then afterwards, those once the grad students leave, the support for that tool or platform may diminish. And the second one is this: that for a community, they require tools, platforms with some more support behind it, and some more engineering emphasis given to it, so that other people can use it too. So that's what resulted in Open Networking Lab, and then after, these are some of the projects that have been going on since then. And if I were to like step away from the lab itself, if I look at the industry, there's like a huge amount of interest in networking or SDN-related products and services. And I think the number of startups that are doing this work are enormous. The first two columns list some of the startups, and these are only the ones which are not in stealth mode. And then there are on the third column is just there are obviously the incumbents who are doing work are working on SDN or are adapting the products for SDN, and then also there are various companies which have been acquired by them, startups which have been acquired by them. So a lot of work that has been going on in the SDN space, and if I were to kind of break it down into the kind of problems that they are solving, and there are each one has a variant to it, but there are roughly 2 or 3 different main classes of problems. The first one, the classic one, is network virtualization, which is to try and is to provide a layer 2 network on a layer 3 substrate, pioneered by I think by Nicira, and then after it's going on from there with many other companies also doing that and enhancing that. Then afterwards, there's been work that's been going on in network function virtualization, which is to virtualize layer 4 through layer 7 services and to offer them as a service. And there's been, it began with a white paper, it did not begin with a white paper, that's one of the things where the term was coined, written by about 12 different service providers and end users, but that has been the second class of problems. And there's another class of problems which I wanted to just pick on, which is called inter-data center traffic engineering. So I've tried to say that what I wanted to say is there are lots of these, every company has their own twist, and there are a number of problems. We can break it down into a few different classes, but let's just take one specific problem and kind of look in that one, and then afterwards see what are the SDN tools and what are the SDN pieces, elements in there, and then afterwards go from there. So this problem that I want to talk about is inter-data center wide area network traffic engineering. If you were to take if you were to think of Amazon or Facebook or Google or Microsoft or Salesforce, and even in the future you can think about enterprises who have got cloud deployments, they have they have a collection of data centers, and these data centers have a huge amount of inter-site traffic, and this inter-site traffic is huge, and it's growing. The annualized cost to maintain this just the inter-site, just the infrastructure that goes into inter-site runs into the hundreds of millions of dollars, be it in the fiber that you lease, be it in the equipment that you have to put over there, be it in the operational cost, and so on. And this inter-site, the kind of traffic that goes on this is basically, in the case of Google, it's a huge amount of, say, search. For search-related back-end stuff goes in. There's a lot of inter-site replication that happens, and for that makes up the traffic component. There's video, there's cloud computing, and enterprise apps. All of those things have a large amount of this traffic. When they use those inter-site WAN links, there's poor utilization on it. The utilization, there's a paper that Google published, actually which came out in the SIGCOMM of this year called the B4. It's on B4 is the experiences with B4, and B4 is their inter-data center backbone. It is the largest production network that is there within, in terms of amount of traffic it carries, it's the largest network within Google. And they found that before they used SDN on all of those things, their utilization on those WAN links were 30 to 40% on the busiest of links. And Microsoft also in SIGCOMM provided some more insight that their busiest links are between 30 to 50%. So roughly you can see the utilization on these links is not significant, is not high. Rather, the utilization is poor. And the reason for that is that the existing solutions, which is MPLS-based traffic engineering solutions, they do not work as well for these type of end users, meaning Google, Facebook, Microsoft, and so on. And they're kind of unique in the sense that they control their application, and they find that there's poor coordination between applications. And this poor coordination between applications results in momentary spikes for which one has to have a more over-provisioned network in order to maintain, to be able to continue service during those spikes. And also there's a MPLS itself does resource allocation in a distributed manner, and sometimes that results in non-optimal allocations of traffic. And
Umesh,
yes?
a quick question. How do you define utilization here?
Utilization of a link would be defined as the bandwidth that the link can carry over the amount of the as a denominator, and on the numerator would be the amount of traffic that is being passed. And what typically people do is that they can measure basically the average. What they would do is you take the traffic bandwidth that is going on a link and kind of plot it over a period of a day or a few hours or whatever, and then afterwards you can see the amount of traffic that has been pushed, and then afterwards you know what the link can do, which is about, say, 10 gigs or 40 gigs over a period of time, and that's how you compute the utilization.
Thank you.
So what do you do by that?
Was there a question?
It's not from the vending machine, obviously.
Oh, I think that someone, I think someone has their microphone or their headset not good.
Okay. I'll continue on. So the way of representing this problem is this, that you have got these 4 data centers, A, B, C, and D, and there are WAN links between each one of them. And say you have an application that wants to, there's an application that has these large elephant flows, and it's asked for like a 20 gig worth of bandwidth from A to C, and given that it's important, it is allocated 20 gigs of traffic. There's another application which is 2, and it wants to send traffic from A to C and asks for 10 gig. But it's only allocated 5 gigs because only 5 gigs is available. This is the kind of way by which end users like Google control the amount of traffic that is used by these large applications and kind of spread out that load over time so that they can achieve maximum utilization and and still be able to deal with high amounts of traffic loads that they require. Now, there have been the approach. So Google built an open flow based wide area network called B4 to solve this, and I would recommend if folks who are interested to read this paper because Google has probably about 2 to 3 years of operational experience on this, and they have put all of those things in the paper itself. But let's see what kind of a solution is possible if we had to use open source software and hardware. And what I want to mention over here is that when I'm trying to put together this solution, I'm using not only the work that is being done here at Open Networking Lab, but I'm also leveraging some of the work that is being done by the Open Compute Project. For folks who may not know, Open Compute Project is something that's been driven by Facebook, and they have specified things like Open Compute specifications for servers, for racks, for data centers, and also they're now specifying and doing an Open Compute specification for a switch. And that is the part that I'm leveraging over here. The second piece of work is the Open Networking Foundation. As you know, ONF is like a sister organization to ONLab, but it's a separate organization. And they handle the standardization of Open Flow. And so there's some work that's been going on that ONF is driving, which is namely a competition for basically an open source Open Flow 1.3 driver, and I'm leveraging that piece too. So I'm going to try and take a few of these pieces put together and kind of show you what is the underlying infrastructure that's needed. The purpose of that whole of this is to kind of tell you how exactly an end user looks at SDN and how does a problem like inter-data center WAN traffic engineering solved using SDN tools and platforms. So this way, when I think one of the key things about SDN is that it shifts the power or the ability to do things from a vendor to an end user, and so we need to look at these kind of end user problems. That's the whole purpose of it. So I would not get too much into WAN traffic engineering, but I really want to use the WAN traffic engineering to talk about the tools and platforms. Okay, so for folks who may not you may have heard many definitions of SDN. I'm just going to use this definition of SDN, which is pretty simplistic. You have the first element of SDN is this, that you have a control plane that is physically separate from the data plane. So the stuff that I've shown below, which is packet forwarding elements, or the data plane is separate from the control plane, which I've shown as a network OS with applications or anything or modules that are running on top of that network OS. The second element of SDN is this, that there's a single control plane that controls several forwarding devices. Now this has the benefit that it is possible to do things centralized where it makes sense to do things centralized, and distributed where it makes sense to do things distributed. Now these are the only two. That's it. That's all how I define SDN. And so it's, in some sense, it is not like a radically new concept or anything like that. I think, but it's just the kind of the abstractions and the way the problems are being able to solve with SDN, especially today's problems, which are coming up with the movement toward cloud. That's where I think this starts to become very exciting. So this is a disaggregated solution that tries to solve the WAN traffic engineering problem. And I'm going to try and I'll describe each one of these boxes. I'll start with just an outline, and then afterwards I'll get into the details. So what we've got is this, what I've shown inside the dotted rectangle is a data center site. Every data center has got racks and racks of switches, be it top-of-rack switches or leaf switches, spine switches, and so on. And right at the edge of the data center, where all that inter-site traffic is actually being moved back and forth, are these data center gateway switches. Now, that is the stuff that I've shown on the right-hand side. Is a data center gateway switch that is built using open source hardware. I'm using an Open Compute switch. By the way, an Open Compute switch doesn't it's a specification that's still coming together, but it is this is something that this will be available by sometime end of the year or beginning next year. So what I'm using is for a data center gateway switch is this open source hardware switch on which runs a say a Linux OS and then afterwards it runs an OpenFlow agent. And this OpenFlow agent lets allows it to be controlled by a controller, by a controller cluster, which is what I've shown on the left-hand side. Every one of these data center sites has this controller cluster. Think of it as basically 3 commodity servers running, again, Linux, and on that, the main application, there's something called an SDN controller, which runs SDN applications. And I've chosen 3 as a minimal configuration just so that we have we have fault tolerance, and also but it can also go up to a larger number if needed, and that gives it that's the scale-out aspect of it. Now, the applications have a not-bound API which connect up to a central TE server. Now, the TE server is what is used within the WAN TE application, within the WAN TE problem to kind of talk to the to provide bandwidth, to handle all the bandwidth allocations and the bandwidth demands from these different applications, and then afterwards push down either policies or flows and stuff like that. So, yep.
Yeah. What's TE?
TE. Oh, sorry. TE stands for traffic engineering.
Okay. Oh, no, thank you.
Okay, cool. So yeah, I'll be sure to to expand on these acronyms in case I use them. There are so many acronyms that folks we use in the networking space that it becomes second nature. Okay, so let's take first as the SDN controller, and that lets me introduce ONOS, the work that we've been doing at Open Networking Lab. ONOS stands for an Open Network Operating System, and it is basically a distributed SDN controller. But let's look at SDN controllers. There have been many SDN controllers out there, and there are some active projects going on in this space only. If you look at the set of open source OpenFlow SDN controllers, the granddaddy is NOX. Then there's been NOX is a C++, C++ based controller that was written by the folks who are at Nicira. And then afterwards there's been POX, which is maintained by Murphy McCauley from Berkeley. There's Beacon, which is one that is developed and maintained by this person, David Erickson. And then after there's another one which is called View, Trema, and so on. The list goes on. Actually, there are a number of these open source OpenFlow controllers that are kind of like written in any language that you would like to, you can think of. There have been a few closed source OpenFlow SDN controllers too. The classic one, the first one is Nicira's, which wrote Onyx. In fact, Onyx is a controller that is, or a derivative on Onyx is something that was written. I think there was a paper on Onyx which has both Nicira, I believe NEC, if I'm not mistaken, and Google authors. Another one which is a closed source SDN controller is HP's Flare, and there are pretty much all the startups and all of those things that I mentioned earlier on. They all have some kind of an SDN controller, and it's likely to be written in a way that is very tied to that application. There are also 2 SDN projects. The first one is Project Floodlight, that's been done by it's maintained by Big Switch Networks, and the second one is Project Open Daylight, which is actually maintained by a consortium of companies, Cisco, IBM, and there are many others too. So there are a number of SDN controllers out there. The time when we started this work, which was around September of this year, Open Daylight was not yet out, and we were looking at these open source SDN controllers, and we felt, gee, all of these controllers are single instance controllers. That means there is just a controller that runs on one server. And if that controller if the application demands were to increase, and what if that server cannot handle it, what is the controller supposed to do? That's kind of a weakness of that of a single instance controller. And the second one is high availability. If that server on which it's running or anything like that should happen, it will bring down the whole network. So I felt that those 2 problems are worth addressing in the open source arena. figure that, yep.
I just want to jump in here, not with a question, but procedurally. Folks, some of you, if I unmute you, I'm getting a lot of background noise and some disturbance, so several of you are muted, and if you're actually trying to ask questions, that might be why you're not able to ask them. So I might suggest the following. Please, mute your own microphones or headsets, etc., so that there's no ambient noise, then I can unmute all of you. Or if you have questions and you find yourself unable to ask them, please, ask the questions via chat. Thank you. Go ahead, Umesh.
Okay, sure. So we decided to, that was the motivation for ONOS, to see if how we can solve the scale-out problem, how we can solve a fault tolerance problem. At the same time, what we wanted to do was that we wanted to retain this global network view, make that kind of a global network view available to these two applications, so that the applications can still be written in a logically centralized manner. With that, I just want to give you a high-level architecture of ONOS, and I'm going to start with the stuff at the bottom and kind of show you what the layers are. And then after I do this one, I will shift to a video demonstration of ONOS in action. So what you see over here at the bottom is a network of 6 switches, 6 open flow switches, but it could be 6, 600, 6,000, that doesn't matter. ONOS runs in multiple instances. I've shown 3 instances over here, instance 1, instance 2, and instance 3. And the ONOS core is actually, we derived the ONOS core out of taking we started with Floodlight, and then afterwards stripped it down to to the bare pieces that we needed. And that ONOS core, the function of it is really to handle the programming of the switches. And it's to do the carrying and feeding of the switches. And then afterwards we've got the whole network segmented so that every instance handles a portion of the network in terms of just carrying and feeding of the switching hardware. On top, in addition, on each one of those instances, we have a couple of distributed structures. The first distributed structure, which I've shown on the top, is a network graph. The network graph maintains the entire network state that is of interest to the switches below or to the applications on top. So if you can think of something like there's a need for a topology, the topology information is maintained in the network graph. If there's an application which wants to provision flows and wants to store these flows so that each one of the ONOS cores can then push them down to the switches, those flows are maintained in the network graph. This is used as a distributed structure. It is shown like this as one big rectangle, but really it is a shard of that, or a piece of that is there on running available on each one of those ONOS instances. So, and we built this using as a backend database. We use Cassandra, and we use it. Cassandra is a distributed hash table. It is a nice way of storing this kind of data. And we use it in an in-memory configuration so that we don't have too much of disk accesses and so on and so forth. And then afterwards, what we did is we layered, we provided a graph abstraction on top of it. We used a graph abstraction because when we started to think about topology and all of those things, we felt graphs would be a useful way of doing that. So there's an open source piece of software called Titan, and Titan is what provides a graph abstraction. At the end of it, what we get is that any application running on any one of these instances can get the global network view by looking in this network graph. And it is, I've called it as eventually consistent state, as you may be aware of, like Cassandra is, in some sense, it's called like causally consistent or temporally consistent, but really it is, what it means is that the state is available in the network graph within a short period of time from the time things are being written by somebody else, or it's a slight amount of delay before that state is available on each one of those instances. The second piece that we have is, yep.
A question has come in online, and the question is, how is the network graph physically maintained? Is it centralized or distributed?
Yeah, so the network graph is actually distributed, meaning there is there's a slice of the network graph. It is so there are, just to back up a bit, Cassandra, it's this kind of the distributed hash table that we used. It lets us specify two parameters. It lets us specify how the data should be replicated and how many copies should be maintained. So we maintain 3 copies of the data, and then that data is striped by Cassandra onto as many available Cassandra nodes as there are. There are 3 Cassandra instances, and so in that sense it gets distributed. The second part that comes up that was asked in the question has to do with access. How, when an access is made, is it local, or can it be a remote access? And that one it's kind of hidden from us. It is sometimes the access could be local, sometimes the access may be remote.
And the second question is there any coherence model applied to this?
Yeah, so the coherence, I think the term that is used over here is consistency model, and the consistency model is, as I was explaining, it is an eventually consistent model. What that would mean is that when some writer writes to say writes a value into this database, and somebody else were to read that value, they may either get the old value for some period of time, and then after that they would get the new value. And if 2 different readers read it, they may some may get the old value ahead of, some may get the new value ahead of somebody else getting the new value. So there's a slight kind of looseness over there. Now that can appear as a disadvantage, but the advantage of that is that it lets us, it makes the database a lot more, increases the performance of the database. So it kind of shifts the problem to an application, but it makes the database more efficient. And we felt this is fine for the kind of state that we show over here, store over here in the network graph, which is really things like switches, link state, and things like that, which naturally have some kind of propagation delay between the data plane and the control plane.
And the Cassandra node actually just, even though you've shown it as one big rectangle, actually is also co-resident on each of those ONOS nodes, correct?
Exactly.
Okay, thank you.
The second piece that is is the distributed registry. This is a strongly consistent data store, and this is built using Zookeeper. One of the things that we use it for is leader election. We have instance 1, 2, and 3, and one instance, and only one instance is the controller is the master for a switch, and the distributed registry is used to elect that leader, and it does that because it has got a strongly consistent database, and so we're able to use it like a distributed lock and establish who should be the leader. And I will show this more when we do the demonstration. So this obviously has got nice properties, but it doesn't perform. It's not as performant. So we use this only for leader election. Also, majority of the state is stored in the network graph. One of the things I want to explain is that we have been using these kinds of open source tools to build ONOS. I feel that none of these quite are sufficient for a networking application. One of the things is that we've derived these tools, which are basically Cassandra was developed for a Facebook by Facebook for a Facebook use case, and they have like large data sets. But if I look at the network state, we don't have large data sets. We have data sets of the order of gigabytes, maybe not terabytes and not petabytes. So we don't need that much of data store, and so the kind of overheads that may go into which Cassandra has in the form of SS tables and this and that probably aren't. If they add overheads, they can be removed, and we can get a faster move. The second thing, which is actually a big gap, is that we need applications to be able to. We need to be able to send updates to applications whenever state changes, and that is something that Cassandra or any kind of database doesn't provide very nicely. And we have to build it using something like, and we are looking at stuff like Hazelcast and Infinispan. They are all of them are slightly different variants, which try different kinds of open source tools which try and provide these things. So notice that we are having to cobbled together a couple of different tools to do this. And what would be nice is if there's like a data store which also provides updates that is more tuned for an SDN-like SDN controller. I don't think there's one out there, but if there is something, I would love to hear about it. So let me do this. Let me now, in the interest of time, let me shift to this video clip of a demonstration of ONOS. We showed this in April at the Open Networking Summit, and it is basically the same thing that I'm going to be showing right now. Okay. Let me get out of this. Okay, and folks, and Sridhar, if you can, are you able to see a new screen which says ONLab ONOS?
Yeah.
Okay. I'm going to start this video, and on occasion I'll pause it. I'm showing this in a video, but at ONS it was done all live. So you know, so this is just a recording of that. This is about 5 minutes. At various places I'm going to pause. Okay, now what you're seeing is a GUI, and I'm going to pause at this point so I can just tell you the brief elements of the GUI so that you'll be able to understand the rest of the demonstration. Okay, I'll pause it. So what you're seeing in the center of the screen is a map of the United States. And on this map you're seeing circles. There are gray circles and colored circles. Let's just look at the colored circles. Every one of those circles is a switch. It's an open flow switch. Now the red circles kind of represent backbone switches. We've got a switch in Los Angeles, in Seattle, Chicago, Atlanta, DC, and New York City. They are actually physical open flow switches. I'll first of all say that, let me say that before I increase expectations, when we did this at ONS, we did not have switches at Seattle, Los Angeles, and all those things. All of those switches were in one rack. So this is being shown more for exemplary purposes to kind of show how it would be in a wide area network context. But all of these open flow switches and all of these things were actually in one rack. So once again, so the physical open flow switches were from HP, Intel, Pronto, NEC, and Netgear. So we had multiple different vendors, and those were the physical open flow switches. But we didn't have, we needed more switches, and so the rest of the switches are actually, the rest of the circles that you see are actually virtual switches, which are you can create one using Open vSwitch. You're seeing a bunch of colored circles, say yellow circles in the DC area. So there's one which is connected to as an aggregation switch, and it's got about 50 edge switches connecting up to the DC area. Similarly, you got a bunch of them which are in Los Angeles and Atlanta. Now, let us shift our attention to the top of the screen. On the top of the screen, you're seeing 4 colored rectangles, and that's ONOS 1, 2, 3, and 4. These are these represent ONOS instances. They're color-coded so that you can match the color of the control of the instance to the color of the switch, which it is controlling. So ONOS 1 is controlling all the backbone switches. ONOS 2 is controlling the aggregation of the edge switches in the DC area, and so on. And what you see at the bottom of the screen is basically flows, and I'll talk a bit more about that in a second. So let's roll the video some more. So ONOS 1 is controlling the red ones. You can see there are totally 106 active switches, and there are 144 flows. We have pre-provisioned flows on this network, and a flow is nothing but is something that is starting from a host at one end to a host at the other end. We're not shown the hosts. And when we bring the flow and show it over here on this on the screen at the bottom, what we are doing is we are showing on the main screen, we are showing the path that flow takes. We have got these marching ants. That means that flow is active. And then afterwards, you're seeing you can see, and under the iPerf column, there is actually traffic that is going on it. What we have done is using iPerf, we have started a like a 1 megabit per second flow, and is showing that flow on that path. The purpose of that flow of that iPerf is just to look at convergence times. So now we're going to do scale out. Imagine you want to add 100 more switches. So you're going to add 100 more switches, and what we'll have is, feel that when you add these switches, those 4 ONOS instances are not going to be enough. So you also want to spin up 4 more ONOS instances. So what we're going to do is we're going to light up those 4 ONOS instances. And what's happening is that they're going to turn from gray to a color, which means that they have come up. Then afterwards, you're going to see also the switches, the circles on the map, which are gray in color, they'll also get turned to color, which means they've been connected to a controller. They've been discovered by the controller, by that instance, and they've been added to this network graph. And as you can see, the number of switches has gone up to 206. Okay. Next is that we're also seeing that the number of flows. We've also gone ahead and added a few more flows. It's right now there are 52 flows. But let's go ahead and add a few more flows. What we're doing with this drag and drop action is this, that it's just a GUI is telling the backend or the REST API to create a flow from a certain DPID of which is a certain some host to another host. And what will be happening is that ONOS will compute the shortest path, install new flow entries into those switches, and then afterwards start an iPerf session to see if traffic is flowing, and you can see traffic has started to flow as I was speaking. So
what's the number on each link, Umesh?
Yeah, the number represents the number of flows that are going on that link. So we have say 96 flows that are between Los Angeles and Atlanta. That's what the number represents. And I think that number will be useful because when we try, we're going to do some link cuts. That's actually the next thing that's going to happen. We're going to remove the link from Los Angeles to Chicago. And when we do that, you've seen that the link is gone, the marching ants have stopped, and then afterwards you can see at the bottom there's no traffic flowing on the 2 link flows that we selected. What ONOS is doing on its own is that it just now it's all of these flows are called maintained flows. That means ONOS will recompute a new shortest path, reprogram the switches, and traffic will start to flow again. And that's what you saw when the traffic started to flow. Let me just back up again because I think it went too fast. So here you found that the link is not there. It is ONOS has recomputed the shortest path, programmed those switches, and then done this. Now, this is in our demonstration. It's taking about 15 seconds. There are ways to bring this down to sub-second, and that's really what's needed in a production network. Now, what we're going to do is show you fault tolerance. Fault tolerance, what we do is this: that we're going to bring down 3 ONOS instances, and we're going to do this by really killing that ONOS instance. And when we do that, the switches will connect to a backup ONOS instance. It will select one of the other ones. When that happens, you'll see the color of the switch change, color of that circle change to a different color. And this color represents the new controller instances controlling it. You saw ONOS 2 went gray, that means it's gone. And then afterwards, all the switches that the yellow, the ones that are connected to DC, they all changed color. Then afterwards, watch the ones near LA. They have changed color, and then watch the ones near New York City. The ones in New York City will, ONOS 8, they will control by ONOS 8, they changed color, and ONOS 8 went gray. So,
Umesh,
and you can see traffic is still flowing. Yep.
There's one more question that's coming online. So the question is, so is the routing protocol applied by ONOS, not standard OSPF or RIP, but some other protocol, some other SDN routing protocol?
Yes, that is correct. OSPF, which is Open Shortest Path First, or RIP, they are all protocols, distributed routing protocols. In our case, what happens is this, that there is a centralized controller, so it is able to discover the topology using something called LLDP. It's a link-led discovery protocol, and it's used to discover the topology, and it has got the entire network graph with it, and so it uses, so we do a very simple shortest path first calculations to calculate shortest path. A variant of A star is what is used, A star or Dijkstra that we use to compute the shortest path.
Okay, I think this may be a related question that you might have answered, but the question is, how does OSPF compute shortest path? Does it use routing protocols how does ONOS compute shortest path? Does it use OSPF or BGP?
Yeah, so as I mentioned, we use, we have the entire network graph with us, and so we do, at this point in time, we do very simplistic shortest path calculations. One of the things that is possible with things like OSPF and all those to like compute like weight-based shortest paths and all of those things, and have and we don't do those things yet. But one of the key differences is this, that the graph calculations are all done in a centralized manner because we have that information all in the central repository. At the same time, it is logically centralized. That is the key part that is different. It's logically centralized because all in this, the Titan-based with the Cassandra backend, it is not kind of distributed as it would be in a typical IP network where every one of these routers is computing or doing OSPF calculations. Now, yep.
In a production setting, and we can take this later, Umesh, in a production setting, you had said that this, when the link between LA and Chicago got cut, you recomputed it. It took about a few seconds, but you had said in a production setting that needs to become sub-second. In a Google-like setting in B4, etc., what kind of latencies do they see when they actually recompute this?
Yeah, they can. They have. One of the key things they use is they program multiple flow entries. So they have multiple flow entries already. They got multiple paths programmed onto the network. So that means they've got a primary path and a backup path. And what they do is they just load balance. In fact, they may not even have primary and backup. They may have like 4 different paths. And they just load balance. In essence, they spray traffic on all of those paths. Should one path were to go down, that they would then spray over the remaining active paths, and then afterwards they'll recompute a new path and create that. So what happens is that you have multiple paths already programmed, and you spray your traffic in a way so that you can keep every flow onto one specific path. So meaning like it's a bit more smarts that are needed, so you don't reorder packets, which is bad for TCP. But that's how Google does it. So the approach which everybody takes. In fact, for example, the reason why when we when we were doing people were doing phone calls, and phone calls are all running over a Sonnet switch, Sonnet provides this ability to restore a path within 15 milliseconds. And the way it's able to do that, and after Sonnet, it is MPLS networks are also able to do that. And the way they do that is they compute a primary and a backup path, and they have both of those paths installed on the data plane, and they very quickly detect a failure, and in they do a local repair. Now, in our case, which is where we are with our implementation, we only have a primary path. We don't have any backup paths programmed on this network. We didn't get to a point where we could implement that. We had wanted to, but we have not yet implemented that. But should we implement a primary and a backup path, we can use OpenFlow's abilities to do load balancing, and then afterwards, and with that we'll be able to get faster recovery times.
Thanks, Umesh. By the way, there are more questions coming in, so do you want me to ask you those now, or do you want to just continue? How would you like to do it?
Let me do this. I think I want to just get through a couple of more things, if it's okay. This way, and I'm going to stop the video at this point in time in the interest of time. I just want to talk a bit about the internals, and then afterwards we leave time for questions once again. Okay, so I want to tell you a bit about the internals of ONOS. So first of all, ONOS is implemented in Java. So this has got a very Java-like organization. We have the key, starting from the bottom up, we have at the bottom we have got things like the packet I/O loop. This is all, what I'm showing is the software that is running on the controller. So we've got a packet I/O loop, we've got an OpenFlow driver, we have an application framework which lets us write different kinds of modules within ONOS, and we have a REST server. Some of these pieces were actually derived from Flatline, especially, in fact, all of them were derived from Flatline. Now, on top of that, what we've written is we've got these things called, you see, path computation, flow maintainer, flow programmer. All of these have to do with programming the switches, computing shortest path, maintaining those flows, and so on and so forth. We also have other pieces which have to do with device discovery, which discover hosts, link discovery, which is to discover links and the link up, and switch manager, which is to discover switches. On the left-hand side is our interface to the network graph. We have something called graph database operations, which is a module that provides various capabilities for, like, say, to write stuff into the network graph or to read stuff from the network graph. You have a registry, which is our interface to this piece, which I was telling you about earlier. We have not yet built an event framework, but that's one piece that we are building right now, which is an event framework lets a module tell another module that something has happened. So such as a link discovery module would discover a link has gone down, and then afterwards, should a flow maintainer be interested in that, it can subscribe to link events and should be able to input receive that. Now, Graph DB Ops and Registry are implemented, and they then afterwards use the Titan library to interface with Cassandra, or the Curator library to interface with Zookeeper. And then afterwards, in the top right-hand corner are different applications. We have ProxyARP. It's an application. ProxyARP is used by the controller to, if any host were to ARP, say, okay, what is the IP address of this MAC, or what's the MAC address for this IP address, it would return that. And then afterwards, we have applications like the one I'm going to talk in the next section called SDN IP, which is using that. So that's in some sense the internals of ONOS. We have, one of the things is we also have, so where in terms of the state of ONOS, ONOS we've been trying to get it ready for we've been doing a few different things. The first one is to make it ready for developers to use, and so it is available to people on the source code is not yet open, but the repository is open on a limited fashion to certain people who want to do some development and do some things with it. And we've also created this thing called a development VM, which lets us do development of ONOS on our laptops, so that we don't need to have like 4 different instances and so on. We can do some of these things all on our laptop. Right, and so that's a development VM has got, basically it lets you create a network using Mainnet, and then afterwards have this ONOS stack all running as a VM, and you can run multiple VMs and test your code and so on. So that's about what I had. So maybe at this point in time, I'll take a few questions, and then afterwards I'll pause again and do the SDN IP piece. Sridhar, you want to?
I guess, yeah, there are 2 questions that came in, so let me ask you those. Is flow defined from one host to another host, or is it computed based, on type of traffic like ICMP, UDP, or TCP?
It's the former, host to host. It is possible to define flows in a more more elaborate fashion. Right now, our flows are just a MAC address to a MAC address, or to an IP address to an IP address.
The second question is, for primary and backup pads, those are dedicated reservations. If yes, is resource efficiency a question?
Yes, absolutely. Resource efficiency would be a question when if we had primary and backup paths. We right now just have one primary path, so we have not yet tackled that problem, and that's a classic. In fact, that's a classic problem when it comes to having multiple paths, because they take up resources, be it flow entry resources on a switch and so on. So managing that is where the is what's needed in a production network.
And you talk about the ONOS apps on the top right with the ProxyARP. Do those, if there are existing apps, do those apps have to get rewritten to sort of adhere to this protocol?
Oh, absolutely. So we have all of these apps at this point. We've been writing our own applications, but yes, an application is nothing but it has to kind of conform to the app framework that we have down below, and it has to be written, and it runs in the same JVM as ONOS. So yes, it has to be written from scratch. And we have, but we have actually, when I talk about SDN IP, I'll show you how we have interfaced with say legacy applications or IP applications, like routing applications.
Okay, thanks. I think we are, the questions are over, but we are about at the end. So Umesh, you said you had a few more slides, right?
Yeah, I think I'll just quickly whip through this one, which will kind of complete the picture. We wanted to, so here's the thing. And as a software-defined network is going to have to exist in Internet of IP networks. That means we need to have SDN be able to peer with IP networks. A software-defined network should be able to peer with an IP network. And if you have to tackle that problem, the way to you have to do that is basically going to have IP routing within an SDN. And the language, the protocol of choice is, as one of the people who asked the question, is really use BGP. How do you, BGP is used to do peering between networks. And BGP stands for Border Gateway Protocol, and eBGP is an external version of the Border Gateway Protocol where there are two different administrators, and they are able to have that to exchange routing information. So we need our software-defined network to be able to speak BGP. And the approach we take is this, that we make our entire SDN network look like one single big router to the IP network, to all the other networks around. And we have so we basically we have a single BGP daemon. This BGP daemon maintains BGP sessions with anybody at all its peers. It computes the RIB, and then afterwards it syncs that RIB over to ONOS. There's an application that we've written, an SDN IP application that we've written on ONOS that takes this RIB and then turns them into flow entries and programs the switches. So the way we implemented this is we did this in partnership with IP Infusion, and that's the reason why we had to use their BGPD. It is possible for us to build this using any other BGP implementation as well. And just we take the RIB, suck it up into this ONOS module called BGP route, and then we have another module which is proactive flow installer that takes those routes, turns them into flow entries, and uses, say, the path computation elements and all those things to compute the shortest path, and then afterwards push these things down. We do some very some important things which are that we are careful about where we store the prefix space. They're like BGP has got a large number of prefixes, and if we have to kind of put prefixes all over the network, it will kind of slow down the reprogramming of our network. So we kind of treat our SDN network as a set of edge switches, which are just the gateway switches, and then afterwards the core, which is nothing but just dumb, and which are, so on those core switches which are inside of the SDN, we don't have to do too much of programming. The reason to do that is that lets us handle a larger number of prefixes and be able to react to them more quickly. In fact, we are doing a deployment of ONOS with SDN IP in the Research and Education Network in New Zealand. On the left-hand side, we've got a couple of REANS production and corporate networks. On the right-hand side, we have the Wellington Internet Exchange, which is a peering point, and we've got about 80 peers that ONOS, or the SDN IP application in ONOS is peering with, and after it's computing the RIB and programming these two open flow switches. So the open flow switch topology is simple, but it's able to, but we're right now stressing the control plane. We're able to scale to around 20,000 routes. We use OpenFlow 1.0. We have this. We'll have this working in about a month or so. Our plan is to finish this by October, and then afterwards we plan to scale it up further. So this kind of is to show that OpenFlow switches and an OpenFlow stack is to kind of get its maturity. So just quickly, I'll touch upon two other things. In the interest of time, you guys can look at the slides and see it. There's Open Network Foundation is working on a driver competition to standardize to get standard implementations for OpenFlow. Everybody seems to be converging on OpenFlow 1.3, and for 1.3, we need to have more controllers which support that. We need to have hardware switches which also support that. And that competition is actually going on right now. 9 people have submitted their code, which is basically this driver code which can be used either as an agent or as in the controller. And one of the key benefits of that is that we'll be able to use a much richer set of functionality coming out of those switches. So that's what's going on. The winning entry will be licensed under Apache 2.0 and GPL. It will be dual licensed, and it'll be able to integrate into a controller or an OpenFlow switch agent. And it will be, you can embed that if you're writing a controller in C, C++, Java, Python, or Ruby. The next piece that I won't have too much time, but I would love to tell you more about, is this Open Compute Switch. But the main elements of this is that it's a specification of a switch which lets us, once we get a Linux, an OS booted on it, we can write, anybody can write their own OpenFlow agent or to flash their OpenFlow agent on it. And with that, this is what we have. We can like think of what we no longer need. You can kind of look at how things have been in the past. We got like specialized packet forwarding hardware, specialized control plane, and specialized features. And what I've done is I said we can build these things, solving those very same problems using these pieces from the open source community, an Open Compute Switch, an OpenFlow agent, and this SDN controller and applications. We are very early on this. We're still a long way to go, but there are some people like the ones at, in these larger companies which have shown that it is possible to do it. So that's all I had.
Folks, any question? So I guess I'll question Umesh with one, which is for folks who might be contemplating doing research in this area, is SDN topic primarily now in the domain of production and engineering issues, or are there still some interesting research problems that need to be solved?
Yeah, I think it's there are lots of research problems. There are a lot of production kind of problems also to be solved. If you were to just look at the number of SDN workshops, there's an SDN activity that's going on, say the SDN World Congress, and then if you just look at the ACM papers, ACM SIGCOMM papers, HotNet, and all of those things, there's a number of research papers that people are publishing. So clearly there are lots of problems. I have been exposed to just to one kind of problem, which is just on the controller side of it, and that too more about trying to build a distributed controller. I mentioned about one other thing, and so I mentioned about the piece that has, I don't think there is a nice data store backend which has got the right consistency model, which also supports updates and also has got these properties. That is more of a semi-distributed system, semi-networking problem, maybe more distributed systems. We've got, I think the kind of problem sets, I just touched upon inter-data center WAN traffic engineering, but within network function virtualization, within trying to do service orchestration, every place I look, I see more and more interesting problems to be solved. And that's the reason why we've got so much of startup activity, and we've got so much of interest in the research papers, in the research community too.
Thanks. Any further questions for Umesh? Going once, going twice. I guess, Umesh, the slides, I'll actually upload them, and so also the recording. I'm happy to share. I think Umesh's slides may have his coordinates as well, so for folks who have follow-on questions, etc., feel free to engage with him directly or route your questions through me. For students and faculty members who have any questions and want to engage with Umesh, feel free to do either approach, to connect with him or through me. Okay. I guess if there are no further questions, then we always do this ritual. Umesh, you might have seen this in our previous webinars, where we give our speaker a virtual clap. So before we go ahead and do that, all of you please unmute your phones or microphones. And as a reminder, our next webinar is going to be on October 25th on demystifying mobile grid computing by a PhD candidate from Rutgers University, Hari Vishwanathan. So I guess please unmute your microphones and telephones, and let's extend Umesh a warm virtual clap here.
Thank you.
Yeah, thank you, Umesh, and I guess we'll see you guys all on October 25th. Thanks so much.
Bye. Thank you, everybody.